So we're in section 8.3. We're going to talk about trig integrals. And this is integrating some of these trig functions. And again, these are ones that are not that do not lend themselves well to use of. So the ones we've studied are something where, for example, we have a cosine squared of x, sine of x dx, which you can rewrite as the integral of cosine of x squared sine of x dx. The use of this, u then would be cosine of x, du should be negative sine of x dx. So now I've got negative the integral of u squared du, which is 1/3 u to the cubed plus c, which will be 1/3 cosine cubed of x plus c. Okay, so this works out real well if I've got, for instance, a single power of sine or cosine. And the same trick would work, exact same trick would work, no matter what the power of cosine is. So for instance, if I was dealing with the integral of, let's turn this around, sine to the 5th of x cosine of x dx, all right, same thing. This is sine of x to the 5th cosine of x dx. Here my u is sine of x, du is cosine of x dx. So I've got basically the integral of u to the 5th du, which will be 1/6 sine to the 6th of x plus c. Okay, so that's nice and simple. So if you just have either a sine or a cosine in a single power, then you've got it made. So what are we going to do then when we face something where they're not all single powers, and they often are not? So for instance, what if we have okay, well now this would be easy if I had just a sine. But I've got a sine cubed. So here's what we're going to do with this. I know I want to have something that looks like this. Cosine to the 4th of x, sine of x. All right, this we can integrate. So this is a simple u sub. But I still have a sine squared of x multiplied out here, dx. Okay. So what people figured out a long time before Newton, and Leibniz ever did this, was actually coming back in and saying, well, this is the Pythagorean identity. Now all I want is just one sine of x. I can use a Pythagorean identity, which is that sine squared of x is 1 minus cosine squared of x. And this comes from sine squared plus cosine squared equals 1. And I just moved that over. So what we do then is we put this in place of this. And if you see what's happening now, I'm getting rid of my signs that I don't want. So now I've got an integral of cosine to the 4th of x, sine of x that I want, that's good. And I'm multiplying that by 1 minus cosine squared of x dx. So what I'm going to do is I'm going to distribute this cosine into, actually I'm going to distribute this whole thing into here. All right, that whole term. And something really nice happens. first off, I end up with cosine to the fourth of x sine of x. That's distributing this into the 1. Well, this is great, dx. We can do this. So now I need to distribute this into this. I'm going to have a minus. And since I've got a minus, I may as well go ahead and break this up and put another integral out there. And now I'm going to have cosine to the fourth times cosine squared. So that gets me cosine to the sixth of x sine of x dx. Now we've got two integrals we can do. My u in both cases is going to be cosine. Du is negative sine dx. So I've got the integral of, negative integral of u to the fourth du. Minus and a minus gives me a plus integral of u to the sixth du. And this is just a nice, simple little rewalk problem at this point. So I'm going to end up with a negative 1/5. U is cosine, so I'm going to have a cosine to the fifth of x plus 1/7 cosine to the seventh of x plus c, and there's my integral. So the trick here is to remember that, excuse me, so if power of the sine is odd, then cosine even. And we're interested in the odd because we can pull them out. Then this is when you pull one sine out. One sine of x out for u sub. And use the Pythagorean identities to turn the rest of sines into cosines. And you distribute, and you've got a very nice little excuse me, a very nice little u sub problem that you can do. Okay. So that's actually kind of nice. So let's turn this problem around just a little bit. And let's say I had a problem of cosine cubed of x sine to the fourth of x dx. And I should recognize this as being the same problem, but I switched my sines and cosines. Here again, the trick here is, this is my odd power. So what I want to do is reserve one of these cosines for that. So I'm going to have integral of sine to the fourth of x cosine of x. There's my u du. And then I'm still left with a cosine squared of x. And then I use the Pythagorean identity. Cosine squared of x is 1 minus sine squared of x. And I convert the rest of these cosines into sines that I distribute in. I have the integral of sine to the fourth of x cosine of x times 1 minus sine squared of x dx. I'm not going to work the rest of this out, but again, you distribute this in, and you're going to end up with a nice little Rewald problem. All right. The only difference here is now u is sine, du is cosine. So we're not going to change the signs. All right. So you've got one positive, one even and one odd. You want to reserve the odd. You want to reserve one of the odds for your u sub, and then turn the rest of the even ones into the opposite trig function. So that you got a nice, easy little problem to do. Okay. So now let's take a look at another example. Now you notice here, I have them both as an even power. And so there's no really nice way to use the Pythagorean identity to turn one of these in. Because no matter what I do when I reserve one, I'm still going to end up with an odd power. And it's just not going to work well. So the way you attack these when they're either both even or both odd, but really especially when they're both even. If they're both odd, try continuing what we did before. We had one of them as an odd power. But if they're both even powers, then you have to use the power reducing formulas, okay? And what that looks like is sine squared of x is 1 minus cosine of 2x over 2. And you can see what's happened is I've reduced a sine now into a single power of cosine, which is nice. And cosine squared of x is 1 plus cosine of 2x over 2. And then I'm going to substitute these in up here. So I'm going to have the integral of, now before I do that, let me rewrite this a little bit. We have sine squared of x, cosine squared of x, squared dx. This is the same thing as cosine to the fourth. So now I've got the integral of sine squared of x, I need to use my power reducing formulas now. The integral of 1 minus cosine of 2x over 2 times 1 plus cosine of 2x over 2 squared dx. Okay, so the way to handle this problem then is you come back in, and the first thing I'm going to do is expand this one out. So I've got the integral of 1 minus cosine of 2x over 2. And then I'm going to have, this is all going to be over 4. 1 plus 2 cosine of 2x plus cosine squared of 2x. And then I'm going to distribute this into here. And 2 times 4 to multiply that is going to give me a 1/8. I'm going to multiply everything in, so I'm going to go ahead and pull this out. And 1 times 1 gets me 1. 1 times 2, so I'm going 1 plus 2 cosine 2x plus cosine squared of 2x. And I'm going to have minus cosine of 2x, which is distributing this, minus 2 cosine squared of 2x minus cosine cubed of 2x. All right, dx. And then I combine my like terms, so I'm going to have a 1 plus, I've got 2 cosine of 2x's here, and then I minus 1, so that's going to leave me with a cosine of 2x. So those I've done, that one I've done. I've got a cosine squared minus 2 cosine squared. There's a minus cosine squared of 2x minus cosine cubed of 2x dx. Okay, now again, and remember I'm integrating this whole thing. Okay, so this one is easy. This one is also easy, since you don't have a power. Remember, you've got to take the derivative, multiply by 2 outside of here. Now this one, you're going to have to use power formula, and I'm not going to do this. But you're going to use the power formula on this again, where you're going to end up with a 1 minus 1 plus cosine of 4x, because 2 times this over 2. And then this one you reserve one cosine, and then the cosine squared left you turn into 1 minus sine squared. Distribute out and integrate it. And that's how you handle these. Now, I'm not going to go ahead and do all of these, but this is basically how you would approach this. Okay. So let's do another example. So I've got the integral of cosine squared of 3x dx. Because my cosine's raised to power, I need a sine x to use a u sub. But I don't have it. And not only that, I've got a cosine squared. Okay? So what do? When you have this, you have to use your power reducing formula. So this now becomes the integral of, everything's over 2, I'm going to pull that out. So now this becomes 1 plus, and remember it's cosine of 2x, but I've got a 3 in there. So it's going to become the cosine of 2 times 3x, which is 6x dx. Okay. This is really easy. It gets you an x. And this gets you a minus. You notice I just got one power, so it's going to be minus 6 sine of 6x plus c. And this is how you do these kind of things. All right? Not bad. Not bad at all. And the whole idea here is when you have it, if you can, is to reduce it down to a single power, which you can do. Or if you can get the opposite, the derivative of it in there, then you can use a u sub. Okay, so the last thing I want to talk about here is what's called Wallace's formulas. These can be very useful. By the way, John Wallace, who discovered this, was Newton's math teacher. And also tutored Leibniz, the two guys who invented calculus. So obviously this guy had a huge influence on modern calculus. Okay, Wallace's formulas. So if I have a single cosine or sine to a power, and what he tells us is if we're going to integrate this thing from 0 pi over 2. Now notice this is definite, and it has to be over this interval. But the integral of cosine to some power of x dx. Okay, now we already learned how to do that back above. But what Wallace did, and if you want to see something which is really kind of neat, look on page 536. And they'll show you how he used the power reducing formulas on these to come up with the formulas he has. It's really slick, and it's kind of a neat trick. And remember, he did this before the Principia Mathematica, before calculus had been formally invented. So here's the two. So if n is odd, and n is going to have to be bigger than or equal to 3. If n is 1, you don't have to use Wallace's, all right? If n is 1, that's just a simple straightforward. Then what you're going to do is it becomes a product of basically n minus 1 over n. So let's say, for instance, if n is 3, and I keep multiplying these out, then I'm going to end up with 2 over 3. All right. And that gives you Wallace's for that one. But let's say n is 9. So I start out with my 2/3. Well, not up there. So then I go back up to the next one, which would be 3. The next odd power is 5. That gets me 4 over 5. So this is for n equals 3, n equals 5. N equals 7 would be 5 over 7 times, and then this is where n is 7. And then I'm going to have, not 5 over 7, 6 over 7. 8 over 9. You multiply all of these out, and you got your integral. Okay, same kind of trick holds if n is even. So if n even, then here we're dealing with n is bigger than or equal to 2. We're not dealing with 0, which is 1. Then what you deal with there is a slightly different one. You're going to be dealing with products of things like 1/2, where n is 2. And then if you have n is 4, then you're going to have 4ths. Okay. And then if n is 6, then this would be 5/6, on, up to n minus 1 over n, where n is your power. And then all of these are multiplied by pi over 2. And that's Wallace's formulas. And these work for sine and cosine. So I'm going to work one example for you. So let's say we're doing integral from 0 to pi over 2. And this has to be the integral you're dealing with. Otherwise, Wallace doesn't work. So I've got cosine to to the 7th of x dx. Now, one thing we could do would be to pull one of these cosines out, right? So I've got a cosine of x, and I'd be left with cosine squared of x cubed. And then you would have to substitute, that would be 1 minus sine squared cubed. You have to expand this, multiply everything out, blah, 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 blah. Okay, can be done, but we just got a single cosine, so I can use him. This is odd, so we start off with 3, which is 2/3. And then I jump up. This is for the 1n equals 3. And then we deal with the power of 5, and I have to have all of these in there up to my power. So then I have 4/5 times 6/7. I multiply all of these things out. I end up with 48 over 105, which reduces to 16 over 35. And like I said, these also hold true for sines, but you have to slap on the pi over 2 at the end of it. Okay, so this will get you started on trig integrals and dealing with some odd powers of sine and cosine. So let's review real quickly the tricks. If I have both sine and cosine, take the one with odd power, pull one out, and use Pythagorean identity to convert to the other trig function. And this works for sine or cosine. If they're both odd, I usually pick the one with the lowest power to pull one out because it means less work on reducing it down. So if they're both odd, take the one that has the lowest odd power and pull one out of that. Okay? So this is if they're both odd, pull your du. Remember, that's what we're interested in. Pull your du function out of the lowest odd power. And then use the Pythagorean identity on the rest of them. All right? And then the other rule we looked at then is they're both even. And there you have to do repeated uses of the power reducing formulas, which are cosine squared of x is 1 plus cosine of 2x over 2, and sine squared of x is 1 minus cosine of 2x over 2. And you may have to do repeated applications of these to bring these down. But there's what we're dealing with. And of course, if you're dealing with something like, if you're only dealing with one power or one trig function to a power, you don't have the other one, then you have to use the power reducing formulas. Convert them all to cosines. and maybe you will probably have to do repeated uses of them. And of course, obviously, if we had an integral from 0 to pi over 2 of a single one, then use Wallace's formulas. And there you go. This is really the last big topic we're going to cover before the AP test.